Hi, and welcome to the second of the RISC-V lectures. In this lecture, we will build on what we learned about RISC-V in the past, but this time we will go over how to actually code in RISC-V, good practices for what it's actually like to write clean code, what the different conventions are for writing an assembly language, and the different nuances of just writing an assembly in general. So as a quick review of what we went over in last lecture, we learned about what RISC-V actually is and something called the RISC design principles. RISC-V was developed here at Berkeley as a simple assembly language. It only utilizes 32 of these so-called registers, which are these pieces of hardware that just contain 32 bits. And all of the instructions in RISC-V assembly language are simply operations involving one or more of these registers. You can consider the registers to kind of be the workbench of our computer and data to be the materials that we need to use to actually, do the work and get things done. And the key idea of RISC is that it's simple. All of the information regarding RISC-V can be fit on one singular green sheet front and back, which you will have access to for the entire course. It will be open out during the exam. You can use it during your homeworks and projects. You're not expected to memorize the green sheet. Rather, it will be useful for you to understand the green sheet and be able to analyze to get the information that you want out of it. One nice thing about RISC-V that kind of draws from C and generic programming practices is that even though we have 32 registers called X0 through X31, we give certain ones special names for clarity. Just like how when you code in real life, you don't want to name your variables random letters and numbers, it's important to have naming conventions that are indicative of what the underlying value is being used for. So in this lecture, we will also go through when to use certain kinds of registers, the S registers, the T registers, the A registers, and if you follow this convention of register naming, it will make your assembly code much, much more readable for us to help you and for you to understand what the heck you just coded for yourself. One of the big things to keep in mind when we deal with an assembly language is that at this point we are at the hardware, so we are just dealing with raw bits. The computer just sees the 32 bits and it is just doing operations on these bits. It does not care what those bits are representing. Remember, bits are just bits. And lastly, a reminder is that memory in our computer models are just byte addressed, which means that we aren't looking at integers and things like 4 bytes, 2 byte kind of things. We are able at the RISC-V level to index into singular bytes with little to no consequence. So here's a quick overview of some of the instructions that we went over last time. We have our very simple instructions, the arithmetic ones and the bitwise and the shift ones that mirror exactly what the C, normal operations do. You can take the values in registers, do some kind of operation on them, and put the result in another destination register. It was very nice, very useful, very straightforward. In addition, we introduced this concept of an immediate, which is basically if you want to encode a constant integer and do an operation with one register and one integer, you can do that as well. So instead of taking the immediate and putting inside of a register and then doing an operation on those, you can just do register, immediate, and put the result there. So anytime you see these I's, just keep in mind it is because it was referring to an immediate instruction. In addition, we went over something called data transfer, which is I think it's one of the hardest things, or the things that it's not intuitive at first, but after a while it's kind of obvious when you have more experience with RISC-V. It's the idea that, when we're working at assembly, we're working at the CPU over here, but all of our data lives in RAM over here. But my workbench is here. So the idea is that we need to get the data and the materials that we want to use. We need to move it, do all the work with our instructions here, and then when we're done, put it back into memory. We only have 32 registers. We do not have that much space or room that we could afford to keep all of our important values here. We need to load and store appropriately. And then last, we went over branching. When we execute assembly, we kind of go down this line one instruction at a time, but sometimes I want to spice things up a little. I might want to go to an instruction that lives 5 instructions away or 10 instructions before or something like that. So we have two options. We have the idea of an unconditional jump and we have the idea of a conditional jump. So an unconditional jump are all of these J instructions, JAL, J, JAL, R, and JR, which basically say you will provide it a destination instruction to go to, and it will simply, when this instruction executes, it will just jump to that new instruction. Now, sometimes we will want to encode higher level logic, such as like if statements or while loops, which is that on a condition, jump to a new instruction. And that's where these branches comes in. Branch if equal, branch if not equal, greater than, less than, things like that. Right, which allow you to basically do an if statement. If something involving these registers is true, then jump to this other instruction. But if it's not true, don't jump, just continue executing like before. As always, all the information regarding these instructions are available on the grid sheet if you ever forget the syntax of any of them. So let's jump into the first concept of today's lecture, which is the idea of sign extension, and this little fancy instruction here called LBU versus LB, and why this instruction even exists in the first place. So let's start off with a quick review. If you remember in the number representation lecture, we learned about something called 2's complement, which was a way of interpreting bits to know if it's either positive numbers or a negative number. So the question is, how do we know based off of some bit sequence whether the number is interpreted as a negative number or a positive number, given that we're working in 2's complement? So here, we have some binary and their respective hexadecimal numbers. Well, how do we know? Well, there's a very simple formula that we can use, or that we should use when we're dealing in 2's complement. I know we teach you the whole, flip the bits and add one kind of thing, but don't forget that underlying 2's complement is a very straightforward formula, okay? It is the normal unsigned formula of just, if the bit is 1, it's 1 times 2 to that power plus, all that other stuff. Okay, the only difference is that in 2's complement, you take the normal unsigned expansion and you negate the topmost bit. So in this case, when we see this number 100010, what we're going to do is we're going to add all of these lower bits here, but then we're going to negate the top bit. We're going to do negative 2 to the 7th here, plus all the rest of the stuff. And that allows us to encode the negative number. So, the natural extension of this is, so now, how do we tell if a number is negative or not? You just look at the topmost bit, the most significant bit. If it is a 1, then it is negative. If it is a 0, then it is positive. As you can see here, right? This is negative, 2 to the something times 0 plus 1 times something plus 1 times something, right? So these are all just getting added. And this is a negative. And even though, so remember that this represents a very large negative number that lives over here. And all the future additions coming from the lower significance bits are just moving that negative number closer and closer to 0. But does it ever reach 0? Well, let's think about it real quick. What is the number that's represented by all ones in 2's complement? It's just negative 1. It's a good exercise. Just convince yourself of it, write down some quick math, and I'm sure you'll be more than happy about it. So all you need to worry about is that if you ever see a bitwise sequence and you want to know if it's negative or not in 2's complement, just look at the topmost number. So the question is, well, let's say I have an 8-bit number and I want to add a bit to it, as in I want to make it a 9-bit number. Okay, well, fair enough. Why might you want to do it? We'll get to that in a second. Hold on. So the question is, how do we do this? Well, in a 2's complement situation, it's actually not as simple as we might think. If you just append a 0, you've actually lost a lot of information. Because if you put a 0 as the new most significant bit, you have actually lost the entire negative aspect of that number. So if I had all ones, let's say here, like I have all these ones here, and then I have 1, 1, 1, 0. If I were to hypothetically extend it by putting a 0 right there, I've lost the fact that this is a negative number. So instead, to sign extend a 2's complement number, we take the most significant bit and we just extend it as far as we would like. So that's why we put an extra 1 here. And the same thing happens if the topmost bit is a 0. If it's a 0, then we know that the number is positive, so therefore we should just be extending zeros. Keep in mind, and it will be a good exercise to show for yourself, that even though we extend all these 1s when we're sign extending here, it's still keeping the magnitude of the number the exact same. We're not making the number any larger or smaller by doing this. As a matter of fact, this 8-bit number is equivalent to this 9-bit number. They both represent negative 2. Okay, very cool stuff in my opinion. Is this the same for an unsigned number? Think about that, and we'll get back to it a little bit later. So one thing that we want to see here is, so how does this take place in a RISC-V instruction? Well, when we use immediates in RISC-V, you are allowed to use both positive and negative immediates. The designers of RISC-V were kind enough to give us that kind of flexibility. However, for reasons we will explore in the next lecture, you can actually only use immediates that can be represented with 12 bits, or these 3 hex digits right here. Okay. However, remember that, when we use these instructions, they need to go inside of a full register. So when I add negative 1 to 0 and put it inside the T0 register, so negative 1 is represented as all 1s, which in 12 bits is just 12 1s. But when I put it inside of T0, what should happen to it? Well, it needs to fill the full 32 bits. So therefore, I should sign extend it. And the same thing happens here, right? Here, the topmost bit is a 0, so therefore I sign extend a 0. And here, the topmost bit is a 1, so therefore I sign extend it as well. So sign extension is happening under the hood in RISC-V when we're dealing with the hardware here. Later on in the class, when you build your own CPU, you will see how this will actually happen. And it's very nice and very convenient to use. What we're most interested in, though, is loads and how those work. So if you remember, we have the idea of a load word, which allows us to take a 4-byte, one word from memory and put it inside of a one-word register. Everything fits nicely. It's just kind of a copy and paste kind of operation. However, we have these other operations, load byte and load half word, where we're allowed to only grab chunks of memory. But what is the issue? The issue is, as we can see here, what if I have a byte, but it needs to go inside of a whole word's worth of space? What do I do with all this extra bits? I can't just leave them to be some random number of bits. It will fundamentally change the value in the register. I need to occupy these bits with values. That way this 32-bit number represents the same thing as this 8-bit number. So what can we do? I sign extend again, right? So when we do these signed loads, all we do is we will load in the byte or the half word. I will look at the most significant bit and I will sign extend it, because this also represents -2. And we can see it as an example here, right? So a normal load from now on, whenever you see LB, LH, these LW technically, these are all signed loads. It will load in the byte right here. It will choose the most significant bit there, it'll kind of put it right there. And then it will sign extend it. And here, the most significant bit is a 0, so therefore it extends a 0 the entire way. Let's look at a quick example. So let's say I have this 1 byte and I'm working in a little endian system. As a reminder, little endian means that the least significant byte, which is 1, 1 in this case, lives at the lowest memory address. And the most significant byte, which is this orange 0, 0, is the most significant, lives at the most significant, or the highest address. My apologies. So if I'm loading the byte that lives at the address pointed to by S0, and I'm offsetting it by 0 here, I'm loading in 1, 1, which is this bit sequence. And if I look, the most significant bit is a 0, so therefore I sign extend the zeros. Now, if I load in the byte offset by 1, I'll be looking here at 8, 0. This is the bit sequence for 8, 0. Noticeably, the most significant bit is a 1, so therefore I will sign extend the 1 all the way through. Now, what if I actually want to have an unsigned number? So let's answer the question that I asked before. Should we sign extend for an unsigned number? The answer is no. And I'll explain why. It's because if let's look at an example here, right? If I'm loading this same byte, 8, 0, and it's represented by this bit sequence 1, 0, 0, 0, okay? The most significant bit is a 1. If I sign extend with all these 1s, is the value the same value in an unsigned interpretation? No, it's not. Because if these were all 1s, I would be adding up all these values, which would lead to a gigantic number, which is not the same value. So in a signed number situation, such as 2's complement, I should sign extend. But if it's an unsigned number, just extend all the zeros. It's as simple as that. We do not sign extend for an unsigned number. So how does this manifest itself inside of RISC-V? Well, if in your C code you decide to declare a variable as, an unsigned int or an unsigned long or something, the compiler will see it and it will instead use an unsigned variant of the load instruction, load byte unsigned. And there is an analogous one for load half word of load half word unsigned. As an exercise, you should think for yourself, should there exist a load word unsigned? Hint, hint, there should not. Now, why shouldn't there be? Well, it's because there's no more bits to fill up. So we don't really care because there's no really sign extension that needs to happen anyway when we do a load word instruction on these machines. So anyway, point is that if we're ever loading in a byte or a half word and we want it to be unsigned and we want to prevent sign extension, use the unsigned variants of these instructions. Fair enough?